something in the device they can manage if it is sleeping or walking, or how they can manage.
We'll talk about all of this. Don't worry.
Asking because I'm doing some research.
So we'll talk about all of this. Of course, I'm not sure if we will be able to answer all your questions, but we're happy to provide more information offline if so scalability. So scalability is another interesting issue because in some applications we need to deploy large number of these sensors to be able to monitor the environment. For example, to measure the growth of fire in the forest or something like this. Sometimes in certain applications we need to deploy maybe hundreds of or maybe thousands of these sensors. So scalability becomes a very important issue. Scalability talks about the fact that if you increase the number of nodes, the current nodes existing in the network will not be affected negatively, or if they are affected, the effect is minimal. So this way you can grow the number of nodes in your system very large without affecting the behavior or the performance of the entire system. In some systems, if you increase the number or the size of the network slightly, then the system will be affected very badly. For example, the spectrum or the bandwidth or the capacity of the network gets divided by the number of nodes. So if you increase the number of nodes very large, then the share of each node becomes very low, and then it does not function properly. So that's not a good design of your system. Your system has to be scalable in such a way that allows the number of nodes in the system to grow very large, yet they can use the spectrum or the capacity of the system efficiently, using some, for example, interference mitigation. So if the nodes are close to each other, we have to divide the capacity. But if they are not in the same interference range, they use the same capacity of the system. So we need to divide the resources intelligently to support this scalability. Wide range of densities. So again, the sensors can be very sparse or very dense, depending on the application and the type of measurements that we need to capture from the environment. For example, in the same application, I can deploy sparse sensor networks. By sparse mean that the distance between the sensors are too far. Okay. Dense meaning that they are very high density, deployed with a very high density, right? So in the same application, maybe I need to deploy a very sparse network to capture some measurements from a large area. Think of, let's say, think of oil and gas field. So I need to deploy these sensors, but I need to deploy them where? I need to deploy a very dense number of sensors or a very dense sensor networks whenever I have condensed infrastructure in this area. So I need more information from this condensed area. But in another area, maybe part of this oil and gas site is deserted, or it does not have, or maybe water or something like this. So in this location, I can only deploy very sparse sensor network to give me some light information, but I don't need to deploy them with the same density, right? So in that case, we end up with a diverse density of deployment for the sensors. It can be, even for the same application, it can be very sparse or it can be very dense, or mixed of both. So again, my techniques and protocols need to be able to adapt to the different densities of the sensor networks. Okay. Programmability, that's another aspect that programmability talks about, the fact that we need to really reconfigure and reprogram these sensors in some applications. For example, I need to add a different dimension or a different type of measurement at some point in the application. So I need some reconfigurability, or I need some flexibility to reprogram these sensors, hopefully in the operation field, without having to collect and redeploy these sensors again. You see what I mean? So I don't need to say, okay, the sensors are deployed now in the field, but I need an extra feature to be, implemented in these nodes. Okay, so I need to collect all the nodes, take them to the lab, program them, okay, and then port all the programs in the nodes, and then redeploy them in the field. That's not efficient, right? So some of these sensors, they have flexibility to be programmed even over the air. So while the sensors are deployed, I can send the program over the air on these nodes. And all of a sudden, now these sensors are programmed to measure different characteristics, or maybe different protocols are implemented, and everything is reconfigurable on the node over the air without having to collect and redeploy. Because always redeploying these nodes is a very tedious and expensive process. It's not an easy process. Maintainability talks about the fact that, again, how frequent I need to go to these sensors and maintain them. Maintain them, including changing the battery, or changing the hardware, the software, whatever. Okay? So these sensors need to be adaptive as much as possible, in the sense that if they can, for example, sense from the environment that the dynamics of the environment is changing fast or it's changing slow. And based on that, they can provide more frequent measurements or less frequent measurements. You see, all these issues did not exist in wireless mesh networks. But sensors have to be intelligent enough to reconfigure and self-reconfigure itself based on the condition, based on the environment. So if the environment is changing a lot, I need to send more measurements. If the environment is not changing a lot, what's the point of sending more measurements? I need to send less frequent measurement. This way I can save some energy. Okay? So, and I need to do this, during like a self-aware mechanism. I need to be self-aware. I need to be intelligent enough to figure out the environment around me, and based on that, reconfigure myself to be efficient for the purpose that I'm doing, or the objective that I'm trying to achieve from sensing the environment. Any questions? Okay, so based on that, what is these are some aspects and some issues that we need, hopefully, to be fulfilled in the wireless sensor networks. So what do I need to have in terms of mechanisms? Okay, what can I do in the wireless sensor networks in order to achieve these requirements? What are the techniques, the protocols, okay, the mechanisms, the algorithms that I need to have in place in these wireless sensor networks in order to address these requirements? So that's what this talks about. For example, I can use multi-hub networks for energy efficiency. We talked about that. So I can leverage the concept of multi-hub to be able to reduce the communication energy. Energy efficient operation both for communication and computation. So energy efficiency is not only through multi-hub. It can be through optimizing the communication protocol itself. We don't need to be, for example, we don't need to use proactive routing, because proactive routing requires what, requires the fact that you have to exchange periodic updates through all the nodes, periodically, right? So we cannot afford doing that in sensor networks. This means that the nodes will be alive all the time and sending route updates all the time. It doesn't make any sense. Okay? So this will consume huge amount of energy. So we cannot do that. So techniques like DSDV, which is proactive routing protocol, cannot be implemented in analysis. The performance for such kind of protocols will be very bad. So communication protocols need to be optimized, and even computation, because also computation is energy consuming, right? So the example that we are talking about, I can spend some time on maybe processing the data, okay, locally, okay, which is okay, but I can do that only if that benefits me. If I don't have any direct benefit from it, then don't do it, because processing will consume energy, and energy is very expensive. Energy is a big commodity in sensor networks. I cannot really waste energy doing any kind of unnecessary processing or communication. So, for example, we have been, in one project, we have been using the concept of adaptive processing to compress the information from the sensors, like for example EEG or ECG or something like this. So instead of communicating these heavy signals frequently, I can just use a little bit of processing to compress them adaptively based on the available bandwidth and the available communication channel and so on. So this way, if I compress more, I will communicate less, right? Okay, so that's a direct benefit. صح? This is a direct benefit. If I process more, compress more, communicate less. So if, assuming that the energy consumption for communication is more than the energy consumption in computation, then there is a direct benefit. It turns out that's a fact. The communication energy is very much more expensive than the computation energy. Okay? Even sensing and actuating is another aspect that I need to optimize, because if I'm sensing more frequently, I'm again utilizing more energy. So I need to sense whenever I have to, or whenever I need actual information to be sent. If I don't need to sense the information now, then I'd rather be in a sleep mode or not doing any type of sensing. So the three components, the three major components that consume energy are sensing, processing, communication, right? And I need optimization in every single aspect, and in some cases combined. I need to combine the energy consumption across these three major components, because they are correlated in a way, right? If you sense a lot, you probably need to process. Otherwise, you will end up with a huge amount of communication, right? So they are correlated. So either you take one component of it and optimize, or maybe two components and optimize, or maybe all the three components and optimize all of them together. Okay? So energy efficiency here takes a holistic approach. Okay? Not necessarily have to address the energy efficiency from one aspect, but rather take this as a holistic problem to try to optimize the energy consumed during sensing, processing, and or communication. Okay. Auto configuration, is it manual configuration? Well, manual configuration may not be an option, because manual configuration means that the person has to go and reconfigure the sensor on the field while it's deployed. Well, this defeats the purpose of smart system and reducing the dependency on the human intervention to maintain these sensors. Okay. Rather, the sensor has to be, again, self-configurable, or needs to use auto configuration, and what it needs to do is that it needs to adapt itself to the environment and use some kind of intelligent technique. So we need some real algorithms to say, okay, the temperature that I received now, they didn't change. So why do I need to communicate it? Okay? And then adjust the sensing frequency based on the changing frequency of this temperature. So we need existing algorithms to do that. So if I sense the temperature every 10 minutes and see that there is no change, then there is no point of measuring the temperature every 10 minutes. Automatically, I need to change this to maybe 1 hour or 2 hours. And if that's not changing, then I need to increase it more. So I need to do that intelligently without having, some person or some human being to come and really do that on the sensor. Collaboration and in-network processing. That's a very, this is a very broad and very interesting field for research in wireless sensor networks. The example that I just said about measuring the average temperature in a very large area, I need to be able to give these sensors a question, and they answer it for me. And the answer requires them to have to collaborate together. And they need to go and collaborate together and give me one single answer. Okay? So if I tell them, for example, give me the average temperature in the whole site, then they measure certain temperatures in certain locations. They have to gather these temperatures in one location. Okay? They sort of fuse this information in certain locations, and it becomes fewer and fewer. They sum all these temperatures, and they report the number of nodes that measured this temperature, and then they bring it to the fusion point to then say, okay, I have the number and I have the summation. I can divide this over this to get the average. See that? Okay. So so they collaborate together in achieving a certain goal. Another thing, or another type of in-network processing, of course, the average here is a very easy calculation. But this can be very complex. It could be that you want to take certain video or certain pictures from different locations, from different angles, and then gather this information in certain nodes that can give you some 3D model of certain areas. So it can be very complex. Okay? Or you can take video and then you can fuse it in a node that maybe combines and compresses the video into one video, maybe using some compression techniques, and then send it forward. So in-network processing can help you to answer complex questions and can also be a very effective tool to reduce the amount of information flowing into the wireless sensor network, right? Because you don't have to have every single node sending huge amount of information to the central point, because this will cause what? This will cause huge amount of bottleneck. And let's just give you some figures to try to appreciate that. So the sensor network is like something like this, and we have the fusion point here. Usually sensor networks, we collect information from the environment and send it to the central server or the fusion node or the sync node they call it. Okay, so instead of having each node sending to the fusion center like this. When I say like this doesn't necessarily mean through one hub, by the way, because this will mean that this node will have to collect from this and this, and will have to collect data from itself, right? So this node collects information from here and here and here. Okay? But each one of these nodes will have a separate stream to send to the central node.
And they are communicating with each one is communicating.
Yeah, they are communicating through multi-hub, possibly.
Then each one have to send.
Yes, but each one has his own data to send to the central node. Okay? But instead of doing that, what I could do is that I can get information from here and here, and before sending, I can actually process data locally and send one stream to the fusion center. And while doing that, I can compress data. I can do all sorts of things. I can compute some features. I can do whatever, okay? And send one stream to the central node, as opposed to 3 separate streams. So in-network processing can be very, very sophisticated, and it could be a very powerful tool to optimize different characteristics in the wireless system.
It's called in-network processing.
Yeah, in-network processing.
And the structure.
The structure of what?
The structure like
The
this
communication.
of the communication.
This is separate from the structure of communication. So the structure of communication, we could use multi-hub, but multi-hub can be used as like separate streams from all the nodes, or we can collect these separate streams at certain nodes and group them, combine them. So you don't have multiple streams anymore. You have only one single stream that's consolidated. But through consolidation, we can do what? We can do compression, we can do analysis, we can do.
So when you're talking about the sensor networks being used in the environment,
Right.
I remember the presentation that I did, the multi-robot systems, which are also to
Mhm.
be used in the environment.
Right.
And they're using like the auction-based protocol for coordination, if you remember.
Right.
So like the most relevant node will send the data or will be asked
Right.
to do a task, and then
Right.
they will communicate with each other.
Right.
So this can be also used for sensor networks, the auction-based protocol.
Yes, this can be a mechanism or one example of a mechanism that's used as part of collaboration, not necessarily in network processing. Because in network processing, as we will see later, it talks about the fact that you have to consolidate, or you have to compress, or you have to do like some coding or something like this.
Some code.
Yeah, if auction means that you combine multiple bidding from multiple nodes and then decide which one to go for,
Auction,
then it's
yeah, it's like you gather information about the robot systems, which one is more efficient to do which task, and they are already sub-classified into categories, like according to their hardware. Or
Yeah, so this is part of collaboration. So collaboration definitely applies there, not necessarily in network processing, because we will talk about in network processing again in details later, and I will show you the different forms of in network processing. This is not necessarily one of them. No.
Even though they collaborate with each other.
They collaborate, yes. Collaboration, yes.
Yeah.
Collaboration, yes. Because these are two different things. Collaboration is something, and in network processing is another thing. So here, the data-centric networking is one of the tools, and this means that we don't need actually identity of the sensor. We don't need the identity of the in the sense of IP, مثلا. We don't need to assign specific IP to sensors. All we need to know is where is this measurement coming from as a location. But we don't need to identify the sensor that did this, right? So that's so to improve efficiency, in many cases we don't even use IP for sensor networks. It doesn't make sense because actually in some of these systems the sensors can get as large as like 1 million. So using IP-based protocols here is not that efficient. And we don't need to really identify every single sensor in the system. We only need to identify where these measurements are coming from in terms of location. Locality means that that you do things locally whenever it makes sense, whenever it makes sense. So you need to process things locally as much as you can and take decisions based on that. For example, if you deploy a camera in a field, so this is one type of sensing. So this camera can capture very high quality video and send it, okay? Or it can capture very low resolution video and send huge, less amount of information, okay? So what the sensor can do in that case is that it can actually analyze locally or process locally the field of view, and then based on whether or not there are some events in this local area, then and only then it sends information to the server. So this helps if you want to detect certain events in the environment, okay? So during normal operation, you don't need high quality video to be streamed to the central server that often. But once there is a suspected event, then you need high quality video because you need to monitor what's going on, and you need to verify, and you need to take some actions, okay? So you can use this to optimize your network. You can use this notion to optimize your network in the sense that the cameras themselves, they are intelligent enough to process things locally. And that will help the camera to decide whether to send high quality video or low quality video. So if there is no event and things are normal, I can send no video or very low quality video because I don't need to monitor anything, because everything is normal, business as usual. I don't need to do anything. But once there is any suspected event, then you need to send very high quality video to the server. Why? Because the server then has to collect from multiple places and monitor and detect very complicated events and based on that take some action. So you should try to process things locally whenever it makes sense. In some cases, it's not advisable. So that depends on the application. Certain applications, if you do local processing, then you gain some benefit. Why? Because based on that, you can decide to communicate less amount of information, and that saves a lot in terms of communication, in terms of spectrum, in terms of bandwidth, in terms of energy, in terms of so many things. Okay? So you can exploit some trade-off between energy and accuracy. And that, again, in the context of measuring more frequent or less frequent data. Because I can, if I measure temperature every 2 days, then the information that I get in terms of real-time temperature may not be that accurate. But if I measure it more frequent, I will consume more energy. So what is the trade-off, or where is the compromise? What is the best frequency in terms of capturing the measurements? Take the temperature as one example, but this applies if you have multiple modalities, multiple types of modalities. Like you can measure temperature, pressure, light, different things. So for each one of these, what is the best frequency to address the trade-off between energy and accuracy? Okay, and in some cases, these modalities are dependent on each other. In some cases, they are dependent on each other. So if one measurement has certain value, then the other one has significance or not. So they are, in a way, dependent on each other. So in that case, you need to address some trade-off on every single measurement, or maybe on all the measurements as a. Okay? So you need to provide or to address some trade-offs a lot in wireless sensor networks. So as a quick comparison between ad hoc and wireless sensor networks, there are many commonalities. There are many common grounds in ad hoc and wireless sensor networks. Again, ad hoc facilitates a bits transfer traffic, just normal traffic. Whereas wireless sensor networks, it facilitates answering questions or capturing environment characteristics. So some of the communication aspects are common. So some of the, especially ad hoc networks, some of them are mobile, in which case they like these mobile devices, for example. They are battery operated, so they have some energy efficiency or issues related to energy efficiency. Not as intensive as the wireless sensor networks, but they have. But these are, designed in such a way that, energy is not that major aspect. Like this can live مثلا for 3-4 days. My mobile phone can live for 2 days. With battery, no problem. I can easily recharge it. I can take it with me and recharge it. But sensor networks is different. So multi-hub is also used in both. However, there are many differences, like the applications, of course. Applications are totally different. For wireless sensor networks, we talked about multiple applications, where ad hoc networks, we're talking about human interaction and sending traffic to across human. Wireless sensor network is very application specific. That's a very interesting issue. Wireless sensor networks depends a lot on the application requirements. It depends a lot on the application requirements, because the application is the thing that tells you what you need to measure. Based on what you need to measure, how frequent you want this measurement to be. Okay? And that dictates the type of communication that you want. Right? And also the application gives you some information about whether you need to deploy these sensors as sparse or as dense network, depending on the environment that you are capturing these measurements from, right? So all these requirements are dictated by the application. And if you change the application, this whole thing changes drastically, right? So this makes wireless sensor network very much application dependent, application specific. That's why the common thing that I always tell my students is that when it comes to wireless sensor networks, there is no one size fits all. One size fits all is not valid in wireless sensor networks. Like we can use this in bunch of different things, and because at the end of the day, what we need to do is to exchange files, and that's it. Okay? But for wireless sensor networks, application is the driving force of all the requirements and mechanisms and techniques and things like that in the wireless sensor networks. The size of the sensor, big, small, the amount of battery, the range of communication. So if I tell you this is oil and gas application which is required to monitor in such a way, then you can tell me, okay, I will design the sensor that big with this battery that live this long, and we have multi-hub with this, and this is a sparse network or dense network. If it's a sparse network, then I need long range of communication. If it's a dense network, then I can use probably like short range, like Bluetooth or something like that. So the whole thing changes. Okay? So when it comes to wireless sensor networks, no one size fits all. That's why I think wireless sensor network is one of the interesting research areas by researchers. Why? Because you can assume that it will last for decades and decades, because every single application requires specific optimization techniques in wireless sensor networks, and that's why in many cases all the papers that include wireless sensor networks, maybe 80% of them will include four such applications. It's appropriate to say wireless sensor networks for healthcare application, or for oil and gas application, and so on. Okay, it's very much application specific. Wireless sensor network talks about environment interaction, as we said. Wireless sensor network might scale from very few nodes all the way to 1 million nodes. So the scale of the network is very, very wide. Whereas for ad hoc, you're not talking about that many nodes in a network. Although maybe nowadays we started to talk about crowd-based networks, or if you have like multiple people in a stadium, and they can communicate with each other using ad hoc. Then in certain applications you can potentially end up with hundreds of nodes as well, but these are very specific applications. But compared to wireless sensor network, ad hoc is not that, it does not scale that big like wireless sensor networks. Wireless sensor networks can scale all the way to maybe 1 million nodes. Energy is much tighter, of course. Energy is much tighter for wireless sensor networks. Dependability on the quality of service. Again, the wireless sensor networks have diverse quality of service, because again the application is the one that dictates the type of services that you want, the quality of this service, and so on. data centric versus ID centric. So the sensor is the sensor networks is data centric in the sense that I don't need to identify the sensor. So when I say data centric, I'm focusing on the data, not on the identification of these nodes.
Is it all the space or only office?
All the spaces.
All the space.
ID centric talks about the identification of these nodes in terms of IP address and identification. So everything is coming from a specific ID, and that's very important because without IP, in ad hoc you cannot communicate. And each node has to have a unique IP address. Otherwise you cannot communicate. I don't care about this in sensor networks. So multiple nodes may have the same ID. I don't care. As long as of course they don't, but I can use any kind of ID, generic ID. I don't need to use IP address in a very long range and so on. I can use any identification. I don't care about identification when it comes to sensor networks.
Don't you need to know the location of the sensor?
The location, not the ID. The ID means like ID, identification.
So it will send you its location.
Yes, I need the location, not the ID.
So the location can be the ID.
The location can be can be an ID, but it depends on how accurate you want this location to be. Maybe you have in the same location you have two sensor nodes, and you don't need to distinguish between the two. You just need to get reading from here or here. It's the same for you. It's the same. So
Data centric is like broadcast from broadcast.
no, data centric. No, data centric means that I need to measure temperature. Okay, whether I get temperature from node number 1 or node number 2 or node number 3, I don't care as long as they are all in the same area. Okay, I don't need to really distinguish that this is temperature from sensor 1 and sensor 2. No, I just need to know that this is the temperature of this location or this room. Okay, so I just need the information. So it's information centric. But ad hoc is ID centric in the sense that this is coming from my iPad. It's very important to know that this information or this file is coming from this iPad or this laptop and so on. Mobility has different patterns when it comes to wireless sensor networks and wireless ad hoc networks. They have different types of mobility and different mobility patterns. There are some, again, commonalities. If you have sensors, for example, in your cell phone, then sensors move the same way with the cell phone. The cell phone is an ad hoc node, and the sensors are part of a sensor network, and they are both moving in the same direction or the same mobility. But in some cases, the sensors can move in a different way. They can be deployed in certain robots or something like that, which can take different roads or different directions, which can be very much random. Ad hoc nodes tends to move in certain lines, or like مثلا vehicles, they move مثلا in certain roads, whether in this direction or this direction or that direction. So there is so they can easily be predicted in some way. But sensors can be either fixed or they can be mobile, and mobility of the sensors do not have to follow certain directions. They can be very random. They can move from one place to another, for example, due to wind. You can deploy them in the in a windy environment, and they can move with the wind or something like this. So they can move very randomly because of the size of the small size of these sensors. So enabling technologies, some technologies in wireless sensor networks that we can leverage and use some existing technologies. Of course, these technologies have progressed a lot nowadays. So cost reduction for wireless communication using simple microcontrollers. So microcontrollers are essentially a small computer with limited hardware capabilities in terms of processing, in terms of memory, and so on. Right? So it's a scaled down computer. And these can be very, very cheap. Okay? And that allows us to design integrated sensor platform that senses and processing things and communicate. Okay? So some microcontroller boards can be easily interfaced with some sensors or some communication adapters or communication modules. So you can easily take these sensor boards, microcontroller boards, interface sensors to it, connect batteries, and connect wireless radio. And this way you have an integrated sensor platform. An example to this is Raspberry Pis, if somebody heard about it, or Intel Edison. So these are microcontroller boards, which are like small computers. They even have USBs and have Ethernet connectivity and so on and so forth. And you can easily interface wireless radio to these nodes. Or you can interface different types of sensors to measure like gas, to measure temperature, to measure a bunch of things. Okay? And these are very, very cheap. So, of course, we cannot afford each sensor node to be a full iPad or a computer. We cannot do that. So we need to use effective cost or less cost for this. Miniaturization talks about the fact that these sensors can be very, very small, because depending on the applications, these sensors can fly in the air, or it can maybe be embedded or implanted inside a person's body. They have commercial implantable sensors in the US, and they have certain laws and legislations that allows them to do surgery to the patients and embed this inside their hearts to measure the condition of their hearts. And if you do that, it has to be, of course, very small, and it has to live, potentially for 10 years, because I cannot do a surgery every week for the person to take it out and put another one. It's not a medication, it's something that requires some surgery. So it has to be of a very small form factor, and yet it has to live for a very, very long time. Energy scavenging is what you talked about, is that we can recharge the batteries through some renewable energy sources. But again, that depends on the application, and it depends on the form factor of the sensor. Some sensors can be designed to harvest energy from maybe the vibrations in the engines in a manufacturing area, or piezoelectric if it's established or set up in the shoe or something like this.
About the smart dust, I'm curious to know how can they use something so tiny to get, like, what kind of information do they get?
As I said, you can implant it in the body of an animal to to get some information from
Like
inside.
what?
Or
Temperature?
yeah, you can know ECG, or you can get some information from the heart.
Something like the size of the dust? They can
Well,
program it
when
to
we
get all
this
the-
is exaggeration. When we say smart dust, we say that it's very very small. But
Like how small?
the dust itself could be like coarse grained or fine grained, right? It can be like a thick dust or a fine grained dust, right?
Yeah.
So the dust does not have one size. So when we say smart dust, we mean that it's very very small. Okay, but it cannot be too small in the sense that we cannot, for example, have a microcontroller, because the microcontroller itself requires size, requires some space. It cannot be really in the size of a dust, in the sense that it can fly in the air and the air can take it everywhere. Although it could be, I don't know, like especially in military applications and for intelligence service and stuff, they could have anything you can imagine. But commercially, I'm talking about commercially, these smart dusts are not widely available, as far as I know. So the smallest sensor I found is like this big.
That's more realistic.
Yeah, so and even with this size, you can have very limited flexibility to interface it with different sensors and stuff. So it's a system on chip kind of sensor platform. So if you manufacture anything that big, then it has to have the sensor and the radio and everything built in. And usually that's not it's not flexible in designing different applications with these platforms. So these can be designed for a certain application. So the whole board is designed for one single application. That's it. But usually people use flexible microcontroller platforms that have different peripherals and different interfacing capabilities that allows you to say, okay, I have this microcontroller board, this is capable of processing with this speed, that's fine. I need my application forces me to use this sensor, so I will interface this sensor with this board, and then depending on the application, I need to use Wi-Fi, so I will connect a Wi-Fi module to it. And then all of a sudden you have an integrated platform for one application. You dismantle this, you collect it differently to fit another application. You see what I mean? So, but usually, if for a small form factor or a very, it will be very, very, very limited.
Yeah,
It will have everything built in, so you can actually theoretically manufacture a sensor and a microcontroller, not microcontroller in that case. Like everything is system on chip, so you can optimize the processing and the sensor and the communication all in a very small board or a very small IC. But good luck, you can spend years to do this, and even then, it's not gonna be this big. It has to be at least this big. Okay.
I think they already have one like the size of a pill, which they use in surgeries to
Yes.
like as a camera.
Oh yes,
for your
that's
son.
possible. But again, I mean, it's a system on chip,
Yeah.
so you have to spend years to do that, and it's not widely used. Why? Because, well, if you spend years to do this, maybe by the time you finish it, the application will change and the purpose and the usage of it will change, in which case you have to go in another round of 2 years to change it. So people nowadays have been talking about reconfigurable computing and reconfigurable hardware. You cannot afford having a piece of hardware that's optimized for one application only. that's very risky in terms of business and market penetration. Okay. So you have a very well-defined application. Okay, so we can stop here.